All right, in this lesson, we're going to be looking at testing for a population mean. So our objective here is just to state and check the conditions for testing a population mean, as well as perform a significance test for population mean, and use a confidence interval to draw a conclusion about a two-sided test about a population parameter. So what we've mainly been focusing on in Chapter 9 is problems that just pertain predominantly to proportions. Now we're going to look at more problems that have to do with means and testing for performing significance tests on that. And you'll remember from the last chapter that when we did a confidence interval with a population proportion, we used z as our critical value. And then when we had a mean and we weren't given the population standard deviation, then we would use t as our critical value. And so when we're performing significance tests, there's really not a ton of difference. So let's just go ahead and look at this example real fast. So a company has developed a new deluxe AAA battery that is supposed to last longer than its regular AAA battery. However, these new batteries are more expensive to produce, so the company would like to be convinced that they really do last longer. Based on the years of experience, the company knows that its regular AAA batteries last for 30 hours of continuous use on average. The company selects a simple random sample of 15 new batteries and uses them continuously until they are completely drained. The sample mean lifetime is 33.9 hours. A significance test is performed using the hypotheses. So let's just say that we were going to perform or find a confidence interval, basically. So let's say that we're asked to construct a 95% confidence interval for the mean lifetime of the new battery. So again, we have parts to our problem of our four-step process, okay? We know that we need to state our population parameter, basically. So we know that our parameter is going to be the mean lifetime of our new batteries. Then we need to we need to plan. So we need to check our conditions. We need to check to see whether it's random, and we're told in the problem that it's random. Then we need to check whether it's independent, and that's the 10% condition. So it's safe to say that 15 batteries is going to be less than 10% of all the batteries that the company produces. And then we also need to discern whether or not it's normal or not. Now, we're not given the data in the problem, but let's say that we're actually given the data and we're not told in the problem that it's normal. 15 is going to be less than 30, so we can't use the central limit theorem for that. So what we need to do is we need to graph the data, basically, and see whether or not it's normal. And it's kind of hard to tell. This is approximately normal, but it's still a little hard to tell whether that's normal or not. But if we look at the box plot or the normal probability plot right here, we can kind of tell that the data is going to be fairly normal, mostly because that all of the data sits fairly close to that line, or it takes a linear form, basically. So since the probability plot is roughly linear, we can assume that the distribution is approximately normal. So again, from there, what we need to do is we need to run a 95% t interval for population mean, and we are told elsewhere that the standard deviation of the sample is 9.8 minutes. So if we're told that it's 9.8 minutes, we know that our sample mean was 33.9. The number of our sample size is 15. So in order to figure out t, what we need to do is we need to use inverse t. So inverse t. And we know that our confidence level is 95%. Well, the area that I need to input for that first number under inverse t, which is under second vars, is going to be the area under the tails, basically, or one tail specifically. So I know that if I have a 95% confidence level, then I have 5% left on both tails of my normal distribution. Well, I only need one of those tails, so that means that I'm only going to have an area of 0.275 right there. Okay, or 0.275. Okay, and I know that my degrees of freedom is just 1 minus my sample size, so I would input 14 for the next number, and that's going to give me a t-value of 2.145. So from there, I would perform my calculation at 33.9 plus or minus my critical value times my sample standard deviation of 9.8, which it tells us right there, divided by the square root of the total number in the sample, which is going to give me a confidence interval of 28.47 to 39.33. So we are 95% confident that the true mean lifetime, and again, this is our conclusion, that the true mean lifetime of the new batteries is between 28.5 and 39.3 hours. So if we were going to actually perform the significance test on this, we have to do pretty much the exact same thing. We have to state for the four-step process, again, the four-step process, we have to state right up there. I'm actually going to erase that real fast. We need to state right here. So we need to identify the population and parameter in question. We also need to state right here. We need to state the null and alternate hypotheses. And the null is there's no change to the population, and the alternate is that there's going to be some change to the population. And again, that can be one-sided, where it's either the mean is going to be greater than or less than the null mean, or it can be two-sided, where the new alternate mean is not equal to the null mean. From there, we need to plan. So we need to state the conditions and confirm that they are met. We need to check to see whether it's random, independent, and normal. And for normal, we can basically perform three tests. We can be told in the problem that the population is normal. We can have a large sample size of greater than 30 where the central limit theorem is met, or we can just graph the data like we saw in the last example and check to see if it's roughly normal. On the AP exam, one important thing to note is that you must show the graph on the test in order to convince the readers and prove to them that you understand that the distribution is actually normal in this case. Okay. From there, we need to do, all of this is the do portion of our four-step process. So we need to calculate the test statistic and p-value. The test statistic is going to be how far an observation is from a mean in standardized units. So we need to basically put in whatever statistic we get from our sample minus the parameter, or whatever mean we're using for our null hypothesis, divided by the standard deviation of the statistic. So the standard deviation of the sample divided by the square root of the total number that's in our sample. Right there, and that's going to give us our t-value, right there, our test statistic. And then from that, we need to figure out what the p-value is, which is the probability that a given observation is likely to occur given a known mean. And that's the area under the standard normal distribution that's outside of the test statistic, basically. And we'll show you how to solve that in just a minute. So the battery company wants to test the null hypothesis that the mean is equal to 30 hours versus the alternate hypothesis that the mean is actually greater than 30 hours, based on a simple random sample of 15 new AAA batteries with a mean lifetime of 33.9 hours and a standard deviation of 9.8 hours. So again, we would need to perform all of our four-step process again. We need to understand that the parameter is the mean lifetime of new batteries with a null hypothesis at 30 hours and an alternate hypothesis at greater than 30 hours. We're also told that the sample is a simple random sample. We can assume that 15 is going to be less than 10% of all batteries produced. And since we graphed the data from before, the normal probability plot was roughly linear. The distribution is approximately normal. So we can solve, or we can do the do portion of this in a couple different ways. First, we can solve the t statistic, or the test statistic, using this formula right here. And then what we can do is we can actually go to second vars and TCDF, and we can plug in whatever we got for that test statistic right there in for the answer. So we can take TCDF and plug in our answer that we found from this formula right here. Because we are checking to see whether the mean is greater than 30, that's going to be our lower bound value. Our upper bound is going to be just a really high number. And then we would plug in our degrees of freedom, basically. So what that would be we have a sample size of 15. We know that our degrees of freedom is just a sample size minus 1, so we would plug in 14 for that. And what that's going to give us is this answer right here of about a 7% p-value, or a 0.073 p-value right there. Now, we can also do this in a much more simple way. We can come up here to stat, we can arrow over to tests, and we can select number 2 right here, option 2, the t-test. And then what we can do is we can arrow over to stats right there and enter in everything that we know about this problem. We know that we're checking a null against a null mean of 30 hours. We know that our sample mean was 33.9 hours with a standard deviation at 9.8 hours. And we know that we had a total number, or we checked a total number of 15 batteries. We also know that we are checking to see we're checking a one-sided alternate hypothesis that's greater than the actual null hypothesis itself. If we calculate that, what we get are these values right here, where it spits out our test statistic and our p-value just right there. So that's a far easier way of calculating that than just having to base it off of your formula itself. But again, this represents the do portion of our problem. So if the mean lifetime is 30 hours, there is only a 0.07 or a 7% chance that we would have a sample of 15 with a mean lifetime of 33.9 hours or more. Let's say that we tested this against a significance level of 0.05. So again, this is our conclusion portion. So conclude. So since 0.0728 is greater than 0.05, or whatever significance level we chose in this case, we will fail to reject the null hypothesis. So there's not convincing evidence to believe that the mean lifetime of new batteries is going to be greater than 30 hours in this case. Now, a couple important things to note about the difference between one-sided and two-sided alternate hypotheses. If we're testing against and how that p-value really looks, or a visual representation of what that p-value actually is. If we're testing an alternate hypothesis where we think the mean is greater than our null mean, what we're really trying to find with the p-value is this area under the curve on the right tail, basically. On the flip side of that, if we were testing to see whether the mean is less than our null mean, then we would be testing to see our p-value would represent the area under the curve on the left tail of our normal distribution. However, it becomes a two-sided alternate hypothesis when it does not equal the null mean. So we're really trying to find the area under both tails of this. So that's when we would have to take whatever we calculate for our p-value and multiply it by 2 if we were doing it the longer way, this way. If we're doing it using the t-test function under stat, then all we would really need to do is just select this option right here in order to figure out what that two-sided alternate hypothesis, or the p-value for the two-sided alternate hypothesis would actually be in that case. So let's look at another example here. Performing a significance test about mu. The level of dissolved oxygen, DO, in a stream or river is an important indicator of the water's ability to support aquatic life. A researcher measures the DO level at 15 randomly chosen locations along a stream. Here are the results in milligrams per liter. So they give us a table, they don't give us much else. But we know that our sample size is 15, and these were the data points for those 15 randomly chosen locations along the stream. So what we're essentially trying to do is a dissolved oxygen level below 5 milligrams per liter puts aquatic life at risk. So what we're trying to find is we have an alternate hypothesis where our mean value is 5 milligrams per liter. Our alternate hypothesis would be a mean value that is less than 5 milligrams per liter, because that's bad. It's not good. So what we need to figure out first is, do we have convincing evidence that at the significance level of 5%, that aquatic life in this stream is at risk? So let's solve for that first. So this is mostly the math. I'm going to come back to that. So again, we need to perform all steps, 4-step right here. So first, we need to state, all of that is the state. We need to state what the population parameter is, which is the mean DO level for the water in the stream. We then need to state our hypotheses. We know that our null hypothesis is going to be that it's 5 milligrams per liter, or 5, what was it? Yeah, milligrams per liter. And our alternate hypothesis is that the mean is less than 5 milligrams per liter. From there, we need to plan. So we need to check our conditions. We are told that the sample was random. 15 is going to be far less than 10% of all of the water in the stream, or 15 points of the water is going to be far less than 10% of all the water in the stream. And then when the data is graphed, so when we plug all of that data in to stat edit, sorry, didn't mean to do that. When we plug all of the data into stat edit right there, what we do is if we plot that right here, we kind of see that we're getting a normal distribution in this point. And this is the point in time where you would actually need to show the AP readers that you understand, that you graph the data, and it came out to be approximately normal in this case. We can also go to one-var stats once we've actually plugged that in to stat edit right here. We can go to one variable stats and figure out our sample mean, our sample standard deviation right here, all that we kind of need in order to solve this problem. So once we've gone over those two parts, we then need to do or perform the do portion of our four-step process, which is to find the test statistic and the p-value for this particular problem. And again, all we need to do is go to stat, arrow over to test, select t-test, and then we've already entered in all the data for our list 1 right here under stat edit. So all we need to do is select the data, input our null mean right there of 5, input our L1 for list, and then make sure that we're checking against a null hypothesis or an alternate hypothesis that's less than the null hypothesis. We would then calculate, and that would spit out our t-value of negative 0.943 and a p-value of 0.181 right there. So again, we would have our, I'm trying to find t, we would have our t-value that's represented by this and our p-value that's represented by this. So since 0.18, and we're testing against a significance level of 0.05, so this is our conclusion portion, so conclude right here. So since 0.18 is greater than 0.05, we will fail to reject the null hypothesis. There is not convincing evidence that the DO level in the stream is less than 5 milligrams per liter, and the wildlife in the stream is not at risk. Now, the second part of the problem asks, given your conclusion to part A, which kind of mistake, a type 1 error or a type 2 error, could you have made? Explain what this mistake would mean in context. Well, because we failed to reject the null hypothesis, really the only type of error that we could have made would have been a type 2 error. So we failed to reject when in fact the DO level in the stream was below 5 milligrams per liter. So that would have been the only consequence to us failing to reject that null hypothesis, is if we were actually wrong and the DO level in the stream was really below 5 milligrams per liter in that case. Now let's look a little closer at a two-tailed test in this case. So at the Hawaii Pineapple Company, managers are interested in the sizes of pineapples grown in the company's field. Last year, the mean weight of the pineapples harvested from one large field was 31 ounces. A different irrigation system was installed in this field after the growing season. Managers wonder how this change will affect the mean weight of future pineapples grown in the field. So right there, right off the bat, we know that our null hypothesis is going to be a mean weight of 31 ounces, and we're testing against a mean weight that is different than 31 ounces. So it could be lower, it could be higher, we don't know. But we're saying that the mean is not equal to 31 ounces in this case. So to find out, they select and weigh a random sample of 50 pineapples from this year's crop. The mini-tab output below summarizes the data, and we're given all of that data right there. And really, the main data that we need to focus on for this is the number in our sample at 50, the mean value from that sample. So we know that from that sample we got a mean weight of about 31.935 ounces and our standard deviation of 2.394 ounces. Everything else we can kind of just ignore for the sake of this problem. Now, in other instances, you may want to hold on to some of that data if this were a different problem. But for this particular problem, that's really all we need to notice, is that right there. So our first part of the problem is, do these data give convincing evidence that the mean weight of pineapples produced in the field has changed this year? So let's go ahead and solve that. We know that we need to perform our four-step process where we state right here, state. So we know that the parameter is going to be the mean weight of all pineapples grown in the field with the new irrigation system, where our alternate hypothesis is the mean weight is 30, or actually it should be 31, I believe. Yeah, 31 ounces, not 30. Sorry about that. And our alternate hypothesis is that the mean weight is not 31 ounces. From there, we need to plan. We need to check our conditions. So we're told that the sample is random in the problem. We can assume that 50 is going to be less than 10% of all pineapples grown in the field. And since our sample is larger than 30, 50 is going to be larger than 30, then we can use the central limit theorem to ensure that the distribution is approximately normal. From there, we need to do. So we need to find our test statistic and our p-value. And how we can do that is, again, go to stat tests and t-test, and we should be able to plug in our null mean of 31 with our sample mean of 31.935 and our standard deviation of 2.394 when we know that the number of our sample size is 50. And then from there, we want to make sure that we are testing our alternate hypothesis against saying that it's just straight up different from our null hypothesis, so it's not equal to our null hypothesis. And what that gives us is a t-value of 2.762 and a p-value of 0.0081. So that pretty much takes care of our do portion of that. But you want to make sure that you show your work by putting it kind of in this format right there, so that the readers know that you know what you're talking about, basically. And then from there, finally, we just want to conclude by saying that since 0.008 is less than our significance level at 0.05, then we will reject the null hypothesis. There is convincing evidence to believe that the mean weight of the pineapples in the field is different than last year, essentially. That's what we're essentially saying by comparing it to that significance level. Now, the second portion of this problem says, can we conclude that the different irrigation system alone caused a change in the mean weight of pineapples produced? And we want to explain our answer. Well, not really, because this test is not a comparative experiment. In this case, the test only tells us that there's a difference between last year and this year's pineapple weights. There may be other factors that's affecting the weight of the pineapple, not necessarily just the irrigation system alone that's affecting that. So that's important to kind of consider when you're looking at that. Now, finally, one last thing. Let's look at kind of the difference between confidence intervals and significance tests as a whole, basically. So let's say that for that same problem, we were given Minitab output for the significance test and confidence interval based on the pineapple data shown before. The test statistic and p-value match what we got earlier up to rounding, basically. So we know that if we were given this Minitab output where they gave us our confidence interval right here, they gave us our t-value, our p-value, all that, we would say that the 95% confidence interval for mean weight of all pineapples grown in the field this year is between 31.25 to 32.616 ounces. And we are 95% confident that this interval captures the true mean weight, mu, of this year's pineapples crop. So, as with proportions, there's a link between a two-sided significance test at a significance level and a confidence interval for a population mean of mu. So for the pineapples, the two-sided test at a significance level of 0.05 or 5% rejects, there's a 5% chance they reject the null hypothesis in favor of the alternate hypothesis. The corresponding 95% confidence level, so 95 is, the flip side of 5% here, does not include 31 as a plausible value. So in other words, because we chose a significance level at 5%, we're going to be 95% confident, then 31 is not going to be included in our confidence interval right there as a plausible value of the parameter mu. So in other words, the test and the interval, basically, the significance test and the confidence interval are going to lead to the same conclusion, where 31 wasn't included in the interval, and we rejected it based off of what we got for P, and we ended up going with an alternate hypothesis. So it's going to lead to the same conclusion about our null hypothesis, but the confidence interval in this case provides much more information or a set of plausible values for the population mean in this case.